Okay, girls, I'm going to go over radioactivity. I've sorted the pen now, so it all works fine. I'm going to go over it again in this way, and only because they're a lot quicker to upload to YouTube or to restream if I do them like this. And then if I do the other ones of an evening or whatever, then I can do the ones which have got more sort of video content in them, only because the bandwidth they need is massive. Anyway, today's lesson is rather complex, okay? So it's really important that you understand it. Now, there's not lots of content today, it's just really important content. Now, with this, I was thinking, well, it's all very well me giving the students these videos and then giving them questions and so on, but what I really need to do for my year 10s is I want to make sure that you've got a sort of a set of notes as well. So what I'll be doing is over the next few days is I'll be working on a set of notes so that you've got something sort of, I'll create something like a PDF. So I don't want any of you to panic thinking, oh, I haven't got a set of notes or whatever. I've got PDF booklets, the school PDF booklets we have, and I can use those to support you, so I've got those. But also I think you need something sort of just to summarise when we've done some learning, something that you can read to and refer from and so on. Now you do have the CGP guides, so obviously they're very good. But I just think I'll be looking at over the next week or so getting something else so that normally in a lesson you see you'll be taking notes and you'll be doing things like that, and you're not doing that at the moment. You're just learning and I'm asking you questions, but you've got nothing tangible that you can hold on to at the end of it. And I know you'd like to, or I imagine most of you would like something like that. So don't worry about that. I will make sure you got something. Okay. All right then. So we're going to be looking at what are called alpha, beta, and gamma radiation. So we're looking first at a nucleus. So if you've got a nucleus, what can happen is this here. So if you think about an atom, inside the atom, you already know that inside the atom you've got protons and neutrons in the nucleus. We did it last lesson, and orbiting that are electrons. Now forget the electrons now, because radioactivity is not concerned with the electrons which orbit the nucleus. It's only concerned with the nucleus. So this here, this part here, represents the nucleus. Okay, so here we've got our nucleus. Now then, this nucleus here is unstable. And when I say it's unstable, what I'm saying is that the nucleus isn't happy with the way it is. It's unstable. It's going to do something. It's going to give off radiation in order to become more stable. Okay? Now, what it can do is it can give off one of three types of radiation, and a given isotope of an element will always give off a particular type of radiation, and then often it gives off another type. So there are three types, and the first one's called alpha. Now, alpha radiation, we spell it like this. Alpha radiation, the symbol for alpha radiation is this. Now, alpha radiation is actually just simply a helium nucleus. So a helium nucleus, just so you know, is that. Now, from last lesson, you'll remember, well, what does that represent? Well, a helium nucleus is simply, you can see from the bottom line here, it contains two protons. So the helium nucleus, or the alpha particle, contains two protons, and because the top number is 4, the mass number is 4, and the atomic number is 2, we know that there are 4 things inside the nucleus. So if 2 of them are protons, then we know 2 are neutrons. Now, this alpha particle is not a helium atom. It is a helium nucleus, okay? A helium nucleus. It is not a helium atom. It is a helium nucleus, okay? So please don't think of it as an atom. It's not, because it doesn't have the electrons which correspond with it, okay? Now, what can happen is, when a nucleus is unstable, it can give off something, it can eject something, and it can only eject one of 3 things. Now, the first one, which is called an alpha particle, which is a helium nucleus, when you think about it, so if you think you've got your 2 protons and your 2 neutrons, these can come out from inside the nucleus. Now, when this happens, they get fired out really, really quickly. It can go about 1/10 the speed of light when it flies out. And this thing here can obviously do damage, okay? So this thing here, when it comes out, it can do damage, it can harm cells and so on. Now, before I go into that, I just want to talk about what it might look like if you asked to explain this with an equation. So a very sort of common example would be something like uranium. So uranium is 238, there's lots of isotopes of uranium, but 238 is quite a common one. Now 92, because that's what makes uranium uranium. Now then, so when uranium decays, what happens is it decays, and it always decays this alpha particle. Now then, you can write 4,2He. It's the same as just writing, it would be the same as writing that, okay? So we've got this alpha particle, so with the numbers on the left must balance with the numbers on the right. So if you think about the nucleus of uranium had 92 protons in it, okay? And it had, what's that, 146 neutrons. Now, what's happened then is, 2 of these protons have gone to here, and 2 of these neutrons have gone to here. So the uranium has changed into a different element, okay? Now, if you think about it, it's lost 2 protons, so we look on the periodic table. Now, on the periodic table, and you'll be given this, by the way, you won't need to find it, it would be thorium, and you wouldn't know that, you'd be given it, okay? So thorium, and the number on the top, so if we've lost 4 things from the nucleus, it would be 2, 3, 4. So we can see this 4 plus this 2, 3, 4 makes 2, 3, 8, and this 2 protons plus 90 protons equals 92. So this here is a very famous decay equation for alpha radiation. So alpha radiation, it can be given off obviously from lots of different isotopes, but this particular one here is quite a well-known one. Now, whenever anything decays alpha, we've got to think about it. If we think about it sort of like this, if we think in terms of, say, X, A, oops, a daisy, and Z. So if this was decaying into something Y, because it is always 4 to He is alpha decay, then the numbers which are missing, this here, this A, that's the number of things in the nucleus, this here is the number of protons. So 2 of this would be Z minus 2, oops, a daisy, and this would be the number of things in the nucleus minus 4, because it's lost 4 nucleons, or 4 things from the nucleus, okay? So that there is a rule for alpha decay. So one thing that can happen when an element is unstable is it can emit an alpha particle. An alpha particle is a 4,2 helium nucleus. You need to know that if you're looking at a decay equation, the bottom number, if you've got alpha decay, the bottom number here will always be 2. And that these numbers must balance, okay? So 90 plus 2 is 92. And this 4, you always have a 4 on the top for alpha, and that number there will be 34 to make 38, okay? Now, the second type of radiation is more complicated, and this is called beta radiation. Now, beta radiation is an electron, and it flies out from inside a nucleus. And I'm just going to show you sort of what causes that. Now, this is quite complicated, and you don't need to know the sort of the first part I'm going to talk about. You don't need to know about it. I just think it is beneficial for students to understand what is going on, because this is quite complicated, but it helps students to realise why the decay equation is the way it is. Okay, so this here is an isotope of what we call carbon 14. Now, carbon, which is number 6 on the periodic table, normally exists as carbon 12. Now, in carbon you would have 1, 2, 3, 4, 5, 6 protons. Now in this isotope, because this number at the top is 14, we can see we've got 1, 2, 3, 4, 5, 6, 7, 8, because 14 take away 6 is 8, so therefore we must have 8 neutrons. And that's what carbon 14 looks like. However, carbon 14 is unstable, which means that it's got to eject something to become stable. Now what carbon 14 ejects is actually an electron. Now you're looking at that and thinking, hang on, there's no electron in the nucleus. So what I'm going to do is I'm just going to show you what actually happens, okay? A neutron inside a nucleus can spontaneously change into, it can what's called decay, into 2 things. Now, this nucleus is held together by a very special force. You don't need to know what it's called yet. It's actually called the strong nuclear force, but you don't need to worry about that. It's held together by this strong nuclear force. Now, a neutron can decay into two things. It can change into, very strange this, it can change into a proton. So this neutron can change into a proton. Now when it does that, if you think about a neutron has no charge. So if it decayed into a proton and a proton has a plus charge, then it must also have a negative charge associated with it, because obviously if you're going from neutral to positive, you need a positive and a negative for it to balance. So a neutron, believe it or not, can change into a proton and an electron. And one way of thinking of a neutron is that it's actually made up of a proton and an electron. Now, this force here, which holds it all together, the strong nuclear force, it only acts on protons and neutrons. It can't act on electrons. So the electron just shoots out with loads and loads of energy, and this here is a beta particle. Now the symbol for beta is like is the Greek letter beta. It's a B with a big tail. Okay, so you get a beta particle. But a beta particle is the same as an electron, as you can see. Okay, so a beta particle is just a high energy electron which has been ejected from the nucleus of an atom. All right. Now let's think about what's happened to the nucleus, and this is very important. If we count the number of protons now, we've got 1, 2, 3, 4, 5, 6, 7, so it's gone up. Now number 7 on the periodic table, in case you didn't know, is nitrogen. Now this neutron, which was there, has changed into a proton, so this neutron's now gone, so that's gone now. So what have we got left? Well, we've still got 14 things in the nucleus, because all that happened was one of the neutrons changed into a proton. So we've still got the same number of nucleons, or protons plus neutrons, in the nucleus. Now, the other thing that was given off was beta radiation. Now, beta radiation is an electron, okay? Now then, you can put the minus if you want, it's up to you. Now then, whenever you have beta radiation, the numbers again must balance. So the top number clearly for beta radiation is a 0, but the bottom number must be 7 minus 1 is 6. So just like alpha, the numbers on either side must balance. So this here, whenever you have beta radiation, whenever you have it, it is always 0 minus 1 E is beta radiation. If I wrote like that, like I wrote the other one before, so before I wrote it in this terms of X and Y and so on. So if you think about it, if we had X, A and X, A and Z, all that's happening is we're going to Y. Now if you think about it, we've got, this is for beta radiation, it's 0 minus 1 E. So this bottom number here would be Z plus 1, and A would stay the same. Okay, so for all beta radiation, every time you have beta radiation, this here is what is happening. Okay, so I'll just recap quickly. A nucleus can be unstable. If it's unstable, it will decay alpha, beta or gamma radiation. Alpha radiation is a 4-2 helium nucleus. That's the symbol. That's the decay equation, an example of which would be this. Or it might decay beta radiation. Beta radiation, I've shown you a little bit much here, I've shown you a lot more than you need to know, just to help you to try and remember, if you can think on in an exam, oh actually yeah, I remember him saying that a neutron changes into a proton, and therefore the number of things in the nucleus remain the same. However, for GCSE, the most important thing is you just literally have to remember that beta radiation, this is the wrong size, isn't it? Beta radiation is equal to, I can't use that because it's just too big, is equal to 0 minus 1 E. It really, really, really is important. And the other one you've just got to remember, alpha radiation is a 4-2 helium nucleus. That's it. Okay. Now the last type of radiation is an unusual one. It's called gamma. Now gamma radiation is easy in one regard because there is no decay equation for it, because it doesn't change the nucleus because no matter is ejected from the nucleus. So if you look at this here, this gamma radiation is an electromagnetic wave. So when we think about this, what all happens is sometimes when sort of an alpha or beta particle is ejected from a nucleus, the nucleus itself is left in what we call an excited state. And in order to become more stable, it ejects an electromagnetic wave, okay? A gamma wave, if you like, a gamma ray. Now, it's just like a high energy photon. It's just like light, if you like. You've done this in the electromagnetic spectrum. It's the most high energy electromagnetic wave. And that's what comes out. Now then, this here doesn't have any decay equations because the nucleus itself doesn't lose any matter. Now, before I look into the penetration properties of these, I just want to summarize some key points, okay? So let's think about it. We've got alpha, we've got beta, and the symbol for gamma is that. It's like alpha facing downwards, okay? Now, let's think about the properties of these things. So, if we think about the charge, because these are really important sort of aspects. So this was 2 protons, so the charge of the alpha was +2, beta was -1, and gamma was 0 because it's just an electromagnetic wave. So let's think about the mass then. So if we think about the mass, well, the mass of the alpha is enormous because it's 4 nucleons. It's 2 protons and 2 neutrons. So its relative atomic mass is 4. Okay. Now compared to the alpha particle, an electron is literally 1/2000th the mass of a proton or a neutron. So it's very, very small. And obviously, the mass of the gamma radiation is 0. All right, so we can see that one's got a massive charge, one's got a smaller charge, and so on, and this has got nothing, and this has got no mass. The mass of this is tiny, absolutely tiny, but the electron does have a mass. So these are sort of the basic properties. The speed of these when they come out. This one here is going about 10% the speed of light, or thereabouts. This one's going about 50% the speed of light, and this one obviously is going about 100% the speed. Well, it is going 100% the speed of light, except for the medium through which it's travelling. So it's probably going about 99% the speed of light in air. So they're going very, very quickly, these things, and because they're moving very quickly, they interact with the matter around them. So let's think about that. So if we think about alpha, beta, and gamma. So if we put a piece of paper in the way of alpha, let's think about this on an atomic level, what's actually happening. Because this alpha particle with its 2 positive charges and its enormous mass is colliding with paper. Now I know we think of paper as being thin, but actually the paper on an atomic level is trillions and trillions and trillions of atoms thick. Now because the alpha particle is physically large and it's got a +2 charge, it's going to interact with the matter inside the paper. And what that's going to do is it's going to make the paper, it's going to attract the atoms in the paper to it, it's going to collide with atoms in the paper, and therefore the paper can stop it. Now, it's stopped by literally, you can stop it with paper, you can stop it with air, just sort of 10 centimetres, 20 centimetres of air is easily enough to stop alpha radiation. Skin is enough to stop alpha radiation. So alpha is very, very easily stopped. It's literally just a few centimetres of air or just a sheet of paper. Now beta radiation, which is the electron, obviously it's got a smaller charge, it's got a negative charge, you'll remember. It's a lot smaller and it's moving a lot more quickly. Now it can go through paper with no problems whatsoever. It can also go through a lot more air, okay? So it can go in air, it'll go up to a few meters because obviously it's going to be colliding with the air and ionizing the air. But normally we say it's absorbed by a sheet of aluminium about 5 millimeters thick. So it will go through really thin aluminium, but if we think about this, not metal, we normally say aluminium in the exams. So a sheet of aluminium about 5 millimeters thick, half a centimeter, is enough to stop beta radiation. It will go through something the thickness of tin foil, for example, but a lot of it will be sort of absorbed. But 5 millimeters of aluminium is enough to stop beta radiation. Now what's strange is gamma radiation, because it's an electromagnetic wave with no mass and no charge, it can't collide with things. It can't collide with atoms, and it's not attracted to atoms. So paper has absolutely no effect whatsoever. It will just go straight through. It'll go straight through aluminium, and it'll also go straight through concrete and straight through lead. Now, what we do say, however, is it will be reduced by thick lead and thick concrete. So it is reduced. It's never stopped, but it is reduced. So it won't stop it completely, but it will reduce it, all right? But we say we can never stop it. We can just reduce the gamma radiation penetrating through concrete, thick concrete or thick lead. It's quite obvious why this is, because the alpha particle is big, massive charge, going a bit slower, so therefore it interacts more with the matter. So therefore the matter absorbs all the energy, so it can't get through the paper. Beta's coming out, it's got a smaller charge, it's moving more quickly, therefore it can manage to get through paper, but it can't get through 5 millimeters of aluminium. And gamma can go through everything because it doesn't interact with it. Now, all these types of radiation are what we call ionizing radiation. Now, ionizing means, obviously you'll know this from chemistry, it means to be able to remove electrons from a substance. So when the radiation interacts with matter, it often ionizes it, so it removes electrons from it. And this can be particularly dangerous when it ionizes human tissue, because that can cause sort of malignancies in cells, and that can cause cancers and so on, which is where we'll be going in the next topic. So I think there's a lot for you to understand there really is. So takeaways are, so my objectives for this lesson are that you understand, okay, it's quite a lot. I want you to understand the properties of alpha, beta and gamma, the penetrating properties of alpha, beta and gamma, and the decay equations for alpha, beta and gamma. Now, I've done this quite quickly, and normally I would do this over a slightly longer time, to be honest, more than a lesson. So, super quick recap. We said some isotopes of some elements can be unstable. This means they are radioactive. In order to become stable, they will emit radiation. There are 3 types of radiation. They're called alpha, beta, and gamma. There is a third, which is the neutron, which we're not talking about today. Now, alpha is made up of a 4-2 helium nucleus. The other one, beta, is made up of an electron. And gamma is an electromagnetic wave. Okay? We also looked at these equations. So because alpha is a 4-2 helium nucleus, as long as the numbers on the left and the right balance, we're able to work out the missing values here. In the case of beta, as long as we remember beta radiation is 0 minus 1, the equations need to balance. You just fill in the missing numbers. As long as they balance on both sides, then we understand what we need to write in this part here whenever we have beta radiation. Gamma radiation has no equations. I then told you about the properties of them, the very basic properties, and then related this to the fact that they can't get through different materials. Alpha can't get through paper, beta can't get through 0.5 centimetre of aluminium, gamma can get through those very, very easily, but is reduced by thick lead or thick concrete. The reason it is so penetrating is because it's got no mass and no charge, therefore it doesn't really attract the matter. Okay? A lot to take in there. You're going to do the questions below just to make sure you really understand everything I've talked about. Now, obviously you may not have understood everything. I will obviously repeat these things and go over them in a different way, give you written resources as well. Please look in the CGP guide, look at any resources you want to, just to make sure that my objective for today is met, which is that the students understand 3 types of radiation. They have 3 sort of distinct properties, if you like, particularly penetrating properties, and my sort of what would have normally be a next lesson actually is that you have an awareness of the decay equations. Now, I'm going to do more work on the decay equations, but I am going to set you a couple of things to see how you get on. All right, so good luck with it. I miss you all, and I'll hopefully see you, well, I don't know when I'll see you actually, to be honest. So take care anyway. Thank you.